In this video, we're going to recall the definition of a topological space and talk more about examples of topological spaces. So here was our definition. If X is any set, a collection tau of subsets of X is a topology on X if both the entire set X and the empty set are elements of tau. The union of any family of members of tau is a member of tau, and the intersection of any finite family of members of tau is a member of tau. In this case, the members of tau are called open sets. Tau is a topology on X, and the ordered pair X tau is called a topological space. So as we saw before, because the members of tau are open sets, that means that defining a topology on X is equivalent to saying what the open sets in X are. So defining the topology is defining the open sets. So recall that in a metric space XD, the conditions 1, 2, and 3 are always true about the open sets in that metric space. So that means that the open sets in a metric space form a topology on X, and therefore any metric space is also a topological space. So the open sets in a metric space are the sets in a topology for that metric space. Let's look at a couple examples. Let's think about the real numbers with the usual metric. So we have the real numbers with the metric D, the usual metric, where the distance between 2 points X and Y is just the absolute value of X minus Y. When we think about open sets in a metric space, remember our initial definition was that an open set is the union of balls, of open balls in that metric space. And so, when we think about that, we've got any point X and then an open X plus epsilon to X minus epsilon. That's an open set. Unions of things like that are open sets, and we were able to show that any open interval from A to B was an open set because we could just union a bunch of those together, and because arbitrary unions of open sets are open, that means that really the open sets in this topological space now are arbitrary unions of open intervals. So we just have open intervals, whatever type we want, e to infinity, etc. And so unions of things of that form are going to be open sets. These are the members of the topology on X, and this could be also considered the real numbers with the usual topology, as well as the real numbers with the usual metric. Similarly, we know that in the real numbers in n dimensions with our usual straight line distance between 2 points, the balls, the epsilon balls in this space are balls centered at points X with radius epsilon, and we could think of that in 2 dimensions or 3 dimensions, and we could sort of theorize what it's like in n dimensions as well. But this is our straight line distance between points, our usual metric for r to the n. And unions of things of this form are going to be open in these sets, or in this space. So unions of things of that form are open. And so Rn with the usual metric is the same thing as r to the n with usual topology. All right, so I'd like you to think about the discrete metric. That's a metric we talked about often. So if X is a set, what topology does the discrete metric give? And when we say what topology does it give, that means what are the open sets? So X is any set with the discrete metric. What are the open sets in X? I'd also like you to think about if X is a set, and S is the set consisting solely of the empty set and the set X. Is this a topology on X? So I'd like you to think about each of these 2 questions briefly, pause the video, and we'll talk about it in a moment. Okay, X is a set. What topology does the discrete metric give? So as we know, the discrete metric, let's call it D, the distance between x and y is either 0 if x equals y, or 1 if x is not equal to y, and therefore the ball centered at x of radius anything between 0 and 1, let's say 1/2, is only the set containing the single element x. So that's the only element in that set. Therefore, singleton sets are open, so this is open. And then if we take any set A that's a subset of x, then A is equal to the union of all elements x such that x is an element of A, right? That's a weird way to write A, but it is the set A, the union of all of its elements, that is the set A. Because arbitrary unions of open sets are open, that means that that is open. And therefore, in the discrete metric, every set is open. So every subset of x is open in the discrete metric. And so what topology is generated by the discrete metric? The topology given by the discrete metric is the collection of all subsets of x. So U such that U is a subset of x. Every single subset of x is open, and therefore every subset of x is in the discrete topology. So every subset of x is in the discrete topology. Now, what about, as you might guess, the discrete topology, that's what it's called, discrete topology, consisting of all subsets of x. We will certainly use this for examples and counterexamples as we continue forward. So let's think about this other one. If x is a set, let S be the set consisting of just the empty set and the set x. Is this a topology on x? So when we're trying to figure out if something is a topology on a set, one way we can do that is just go to the original definition. What are the qualities of being a topology? The first one is that the empty set and the entire set are elements of the collection of sets, the topology. So yes, that's true by definition. 2, for any arbitrary collection of sets in S, their union is in S. Is that true in this case? Well, we could union the empty set with itself, and that's an S, great. We could union the empty set with the whole entire set, and that's the whole entire set, and that's in the set, that's great. Or we could union the set with itself, and that again is X, and that's already in S, so great. And similarly, is it the case that any finite intersection of sets in S is in S? Yes, this is true as well. We could do the same thing that we looked at above. Empty set intersected with itself. Empty set, yes, that's an S. Empty set intersected with X, that's the empty set, and yes, that's an S. And X intersected with itself, that's X, and it's in S. So if we take, and we could union or intersect those things together multiple times, and we'd still have the same result. So yes, this set containing just the empty set and the set X is a topology on any set X. And it's kind of like the opposite of this one, right? So X could be the set of all real numbers. And we say that the topology, this topology on the real numbers is defining the open sets of the real numbers to only be the empty set and the set X. That is a topology on the real numbers, and it's kind of the opposite of what we have up here, which is where every set is an open set. In the one we're talking about right now, only 2 sets are open, and that's the empty set and the entire set itself. So this is kind of like the opposite of what we have up here. And so this topology is called the indiscrete topology on X. So any set X, no matter what, is always going to have at least two topologies defined on it: the discrete topology, where every set is open, and the indiscrete topology, where only the empty set and the entire set are open. Here is one more topology that is a topology on any set X. It's called the finite complement topology. And so if X is a set, let's let T prime be the collection of subsets of X such that U is equal to the empty set, or the complement of U complement, or X minus U, is finite. This is a topology on any set X, and it's called the finite complement topology. So we'll use it often as an example or a counterexample. So I would like you at this point to pause and use the definition of a topology to think about why this tau prime, or T prime, the finite complement topology, is a topology on X. So pause and think about that for a moment. All right, so we're saying X is a set. Tau prime is the collection of subsets of X such that X minus U is finite, U complement is finite, or U is equal to the empty set. This is the finite complement topology. Let's prove that it's a topology on X. So the first property of a topological space is that the empty set and the entire sets are elements of the topology. So we want to show that that is the case. Let's see. So by definition, we already see that the empty set is in tau prime. So great, we've got that already. And now let's consider X. Then X complement, or X minus X, is equal to the empty set, is a finite set, right? It contains 0 elements. So because X minus X is finite, because X complement is finite, that meets the definition of being in tau prime. So that means that yes, X is in tau prime, again by the definition of tau prime. So great, we have this property. 2, we want to let U alpha be some collection of open sets, or some collection of sets in tau prime. Let U alpha be a collection of sets in tau prime. This is some arbitrary collection. It could be an infinite collection, or a finite collection, or an uncountably infinite collection. We want to show that the union of the U alphas is also in tau prime. We want to show that arbitrary unions of elements in tau prime are in tau prime. So, in other words, to show that it's in tau prime for this particular topology, that's equivalent to saying that we want to show that the union of the U alphas is either equal to the empty set, or the complement of them is finite. So, or X minus the union of the U alphas is finite. That's the definition of what it means to be in tau prime. So we want to show if the original sets are in tau prime, their union is in tau prime. Okay, we've got 2 cases here. The first is sort of a silly case, case 1. That would be that U sub alpha is equal to the empty set for each alpha. For all of those sets are actually equal to just the empty set. Then in that case, the union of all those U alphas is also equal to the empty set, which is in tau prime, and we're done. So that's case 1. Case 2, at least one of those sets is not the empty set. Let's say U sub alpha I is not equal to the empty set for some U sub alpha I in this collection. Then let's think about, well, we want to show in that case that the complement of this union of sets is finite in order to show that this is in the finite complement topology. Then X minus the union of the U alphas, how could we write that? Well, by De Morgan's laws, which we covered way earlier in the course, but by De Morgan's laws, that's equivalent to the intersection of x minus u alpha for each alpha. De Morgan's laws says that in general, the complement of the union is the intersection of each of the complements and vice versa. So De Morgan's laws takes the union or the intersection outside and flips the sign. So, okay, great. Now what can we say about that? This is the same thing as the intersection of the U alpha complements. So the intersection of a collection of sets is the subset of any one of them, right? So this is a subset of U alpha I complement. And we said that U alpha I was not equal to the empty set. So since U sub alpha I is in tau prime and U alpha I is not equal to the empty set, the definition of being tau prime is either it's an empty set or its complement is finite. So x minus U alpha I is finite, and therefore this is finite. So what we have is that x minus the union of the U alphas is a subset of U alpha I complement is finite, and therefore that means that the union of this collection of sets is in tau prime. The last property of being a topological space is that the intersection of elements of the collection is also in the collection. So let's let ui be elements of tau prime for 1 less than or equal to I less than or equal to n, and we want to show that the intersection of the ui's is an element of tau prime, again from I equal 1 to n. That can either mean that i.e. the intersection of the ui's is equal to the empty set, or x minus the intersection of the ui's is finite. Those are the two ways that this set can be in tau prime. So again, we're going to get sort of a weird case out of the way where one of the sets is equal to the empty set. Why do we have this case in this particular situation? This will not always be the strange case for showing any collection as a topology. Here it just is because, again, tau prime are sets that have either the property that the set is the empty set or that its complement is finite. So we're sort of getting rid of this case and then considering the rest. So case 1, ui equals the empty set for some I. Then the intersection from I equal 1 to n of the ui's is also the empty set, and that's automatically in tau prime by definition. Case 2, ui is not equal to the empty set for any I in 1 to n. So in that case then, we want to show that x minus the intersection of the ui's from I equal 1 to n is finite. We're again going to employ De Morgan's laws. So De Morgan's laws say that if we instead of taking the complement of the intersections, we can break that apart and say that I equal 1 to n of ui complement is equal to the union of the ui complements from I equal 1 to n by De Morgan's laws. And, well, what do we know? Because none of the ui's was equal to the empty set, that means that ui complement is finite for each I, since ui is in tau prime and ui is not equal to the empty set for all I. If it's in tau prime, it either must have a finite complement or be the empty set, not the empty set, so they each have finite complements. we know that the finite union of finite sets is finite. We proved that as well earlier in the course. Just as a reminder, we could let M be the maximum cardinality of these UI complements, and then the cardinality of the union of the UI from I equal 1 to n, well, that's less than or equal to m plus m plus m plus m n times. That's less than or equal to n times m, and that's clearly finite. So it's just on the side. So the finite union of finite sets is finite. So therefore, x minus the intersection of the UIs from I equal 1 to n is finite. And so that means that the intersection from I equals 1 to n of the UIs is an element of tau prime. So we've shown that the empty set and the entire set are in tau prime, that arbitrary unions are in tau prime, or arbitrary unions of elements of tau prime are in tau prime, and finite intersections of elements of tau prime are in tau prime. So tau prime is a topology on X for any set X. So if we have a set X which is infinite, the discrete topology, the indiscrete topology, and the finite complement topology are topologies on any set X. Note that if X is finite, then X minus A is finite for all X, or for all sets A. And in that case, then the finite complement topology is actually the same thing as the discrete topology, because every set has a finite complement, therefore every set is open, and then we're just back to the discrete topology. So if X is a finite set, then the finite complement topology and the discrete topology are actually the same thing, but if X is an infinite set, then they are not.